This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Welcome to Software Engineering Radio. I'm your host, Gavin Henry, and today my guest is Luca Palmieri. Luca Palmieri is the author of Zero to Production in Rust and focuses on back-end development, software architecture, and the Rust programming language. He works at MainMatter as a principal engineer consultant. He was formerly at AWS, TrueLayer, and has been part of the Rust community since 2018, which is a long time. When he's not coding, you'll find him baking cakes or rolling pasta sheets. Nice. Luca, welcome to Software Engineering Radio. Is there anything I missed in your bio that you'd like to add?
I would say that's pretty accurate. And first and foremost, thanks for having me. I think probably the only thing that's missed is I'm an open source software developer as well. So I maintain a variety of projects on top of my employment duties. Let's call it that way.
And is that quite Rust heavy or just a good mixture?
Primarily Rust, I would say, at this stage, at least the ones I'm actively working on.
Excellent. And when was the last time you made pasta sheets?
That must have been a couple of weeks ago. So not that long ago.
Oh, that's cool. Yeah, I got you on the show because I really enjoyed reading your book, which we've mentioned in the intro, Zero to Production in Rust. It helped me understand some sort of specific Rust development practices in relation to the back end. So I'd like to talk about that, if it's okay with you.
Yeah, more than happy to.
So to begin with, I'd like to have an overview in your own words of what production Rust code is.
So I would say that in one way, it's not very different from production code in any other language. There are some specific operational challenges that one must prepare for whenever it deploys any kind of software in a production environment. You need to know when it fails. You need to be able to restore it to a good state. You need to be able to keep an eye on warnings and understand what's going on without necessarily being able to print line debug or try to do things that mess up with the state of the software. Then the Rust aspect of it is how to accomplish those non-functional goals, if you want, using the tools that the Rust ecosystem provides and the Rust programming language provides. So it's how to decline all these solutions and all these challenges in the specific context of Rust. That's the kind of gap, the niche that the book tries to fill.
Perfect. And can any Rust code be put into production, or is there a certain technique you have to do when you create it or compile it and build it?
Generally speaking, deploying Rust code is fairly easy insofar as Rust binaries tend to be self-contained, plus minus the occasional system library dependency. If you're linking into some C libraries like compressions or some TLS libraries. So bringing Rust into production can usually be done either by shipping the raw binary, which you can compile for the architecture you're supposed to deploy to, or by shipping a very minimal Docker container that contains the Rust binary. Which is pretty nice because it makes Rust production deployments fairly lightweight. The images are small. You don't have to ship at runtime as you would do if you were shipping a Docker image of JavaScript or Python or C#, for example. So that makes them quite nice also in environments like serverless when the size of what you're trying to deploy matters for cold starts and similar concerns. But yeah, generally speaking, is you need to compile your code into an artifact. The process is fairly straightforward. And then you push that artifact in whatever way the platform of choice you picked likes to be ended artifacts. That could be in a Docker container, that could be in a zip file, that could be an FTP if we are doing something the old-fashioned way.
Is there a specific Docker image that you recommend that people should use? Because it's based on a base image type thing, isn't it?
Yes and no. So when you build Rust Docker images, you're usually doing what's called a multi-stage Docker build. So you'll have a first stage where you are compiling your artifact. In that stage, you'll need the tool chain. So you'll need Rust compiler, you'll need cargo, potentially additional tooling, depending on the specifics of your project. But after that stage, the only thing you care about is the binary that's being compiled. So you would normally then copy that from the first stage to a second stage. And the second stage wouldn't have anything that is Rust specific. It would only be a base image, which depending on your constraints might be something like a Debian Slim base image. It could also be a distroless base image. And if you are particularly concerned about the size of the image, you would even push it on a Scratch image. So really, you don't need much beyond the operating system and whatever, as I said before, system dependencies you may have. So if you depend on OpenSSL, you need to make sure that OpenSSL is in your runtime layer. But other than that, really, like, you're free to pick whatever operating system you prefer.
There's a concept of profiles, isn't there, in Rust?
Yes.
What would you pick for production code?
So for production, usually you'd pick, so for those who haven't used Rust before, there's two default profiles, dev or debug and release. Debug is optimized for fast compilation at the cost of runtime performance. So programs programmed in debug will generally be a lot slower than programs programmed in release. Release takes longer to compile, but squeezes out more performance in the final artifact, and usually the artifact is also smaller. So generally speaking, you would go off with the release profile. You can further customize it. There are things that you can enable and disable depending on what you're trying to achieve. You could, for example, choose to include the bug symbols in your final artifact if you want to do something like collect stack traces in production. You could choose to minimize the size of the binary, perhaps exchanging it for some performance penalty. You could choose to do link time optimization of various kinds, which could result in higher runtime performance. You could do something like profile-guided optimization if you have collected traces of your application running and you know which paths are hot and which paths are cold. So the baseline is that release will be good enough. And then from there, you can do a bit of release engineering to try to tailor the profile to your specific needs. But that's generally something that doesn't matter for first deployment.
Could you just take me through those last two again? I didn't quite understand. I hadn't heard them before.
Link time optimization is something that relates to the way compilers usually link together multiple libraries into one final artifact. So if you are looking at Rust, where you compile your Rust application, this Rust application will usually have a dependency tree. The dependency tree will be composed of libraries that might be your libraries or third-party libraries, which can number in the tens, in the hundreds, in the thousands, depending on how complex the project is. The Rust compiler compiles each of those dependencies on their own. We say that the crate is the compilation unit. So every library is compiled into an intermediate artifact, and then those are linked into one at the end. This may cause the compiler to miss some optimization opportunities. A common optimization that compilers try to perform is inlining. So if your function calls another function, but the function is very short, perhaps the compiler might remove the indirection and just inline the body of the second function directly into the body of the calling function. Trying to do these optimizations across the crate boundary can be difficult. And this is a trade-off between compilation performance and the performance of the final artifact. By splitting the compilation into smaller units, independent units, the compiler can compile different units in parallel. So it allows you your final artifact to be built faster. But by splitting them up, it may miss these chances to try to squeeze a little bit more performance. So Rust has two options, really. One is the compilation units, and the other one is the link time optimization, which you can configure to try to recover these optimizations at the cost of significantly longer compile times.
And the crate is a Rust library, isn't it?
Yes, the crate is a Rust library. The other I was talking about is profile-guided optimization. By the way, none of these things is specific to Rust in general. You'll find similar concepts also in C++ or generally anything that is compiled. So profile-guided optimization refers to using runtime information to optimize the final artifact. So when the Rust compiler looks at your application, it doesn't know that 99.9% of the times, for example, where folks try to hit one of your authenticated endpoints, the authentication will be successful. So it doesn't necessarily know that the error path will be invoked rarely. So it assumes that all branches with some caveats are equally likely, and so compiles the program without making any specific assumptions. What you can do is you can collect some runtime information. The specific formats for doing this, also not an expert necessarily in the technique, but you can collect this runtime information. And then when you compile your artifact, you tell the compiler, look, this is what this program usually does at runtime. And so the compiler can then use that runtime information to say, well, let me make it so that the stuff that's commonly used is as optimized as possible, perhaps penalizing a little bit some other code paths. This is something, for example, that the Rust compiler does to optimize itself. So when you download a binary of the Rust compiler on Linux, that is profile-guided optimized. So they have collected runtime traces of compiling Rust programs and then use those to optimize the compilation of the Rust compiler itself, squeezing out a few percentage points of performance, if I recall correctly. So it's a technique that if you are really trying to get the fastest binary possible, it's something that should be in your portfolio of optimizations.
Yeah, that's something I've not come across. I've done quite a bit of C as well, profile guided optimizations. And that's not specific to Rust.
No, I mean, it comes from LLVM, the underlying machinery that Rust uses to generate native code. So anything that uses LLVM, I suppose, should be able to leverage PGO.
I'll put something in the show notes with a link to that page on the LLVM website. Excellent. So are there any specific features of Rust that we need to consider when building a production-grade application that we've missed?
Features in particular, I wouldn't say so. There's patterns that you need to be aware of, which we may touch later on, like the way you handle errors, the way you handle logging those errors, the way you handle panics, for example. But generally speaking, I would say there's no specific language feature that you need to be mindful of.
Perfect. Okay, I'm going to move us on to our next section, which is to explore a complete app and then go through a few bits in your book that were new to me and I really enjoyed. So in your book, you take us through a complete application from development to production, and it's really enjoyable to see that workflow and understand the different bits of it, because usually you just see this is how you do the Rust bit or this is how you do that bit. And so it's nice to see a whole A to Z of that workflow. So what does the app do in your book?
So it's a very, very simple newsletter management application, which you can use to send newsletters out to subscribers. It's complex enough that we need to care about authentication, database management, a little bit of front end, like the bare minimum. But simple enough, as you say, that in roughly 600 pages, we can go from absolutely no code to a reasonably complete application that fulfills the spec that we set out to build. So we are able to send emails out, we're able to add subscribers, we're able to verify their emails, we're able to verify that the person who's sending the newsletter in is actually an admin. All those little key functionality that you almost always find in any production application.
And it's sort of API based, isn't it? Web API.
Yeah, mostly we focus on the back end because the front end, especially when the book was first written, so a few years ago, there wasn't really much about Rust on the front end beyond using Rust as WebAssembly modules. Now, there are a bit more Rust front-end frameworks at this point in time, but still my recommendation would be to stick to more consolidated choices, unless you have a very compelling reason to try to push Rust into the browser.
Yeah, it shouldn't really matter what's in the back end if it's just API-based. Just pick whatever framework you want.
Yes.
So in your book, you talk about an inner development loop. Could you take us through what you mean by that?
So the inner development loop is the cycle of actions that you perform on your local machine to validate what you're doing. So in a language like Rust, this might be, I have my editor open, I am trying to implement a little feature or a little piece of functionality. So I'll write a bunch of code, and then I'll want to check if it compiles, and I'll want to check if I've written any tests, if it passes the tests. And I want to be able to do this as fast as possible, because the faster I can get feedback, the faster I can iterate on any mistakes or move on to the next task. And this is really a concept that ports to any language. In other languages, they may not be compiled. So for example, if you're working with Python, this would be trying to execute the tests and perhaps do some explorative debugging or explorative usage of the application to make sure that it works. Now, since Rust is compiled, that makes it so that generally this inner development loop is going to be slower than a dynamically typed language because you have that compilation step. So what you want to try to do is you want to try to organize your project in such a way that we try to minimize this penalty. So we try to make the compilation as fast as possible. We try to break down our project in smaller units so that they compile faster independently. And we try to keep our test suite fast. Generally, that is the goal, to maximize the number of iterations that we can do per unit of time.
And you touched upon the structure of your Rust project there. I can't remember if it was your book or somewhere else. I'd read some tips on having lots of different files and working on the one file because that's the only one that will change. So the Rust compiler won't build everything again if it was all in one file, as it were. Did I understand that?
Unfortunately, that is not true. That goes back to what we were discussing before around the way Rust compiles a project. So the unit of compilation is the library, is the crate. So if you change one file inside one crate, the Rust compiler will still have to recompile the whole crate. Now, this is not a complete recompilation. So the Rust compiler supports incremental compilation, where it'll save a bunch of information from the previous compilation attempt to try to speed up the next compilation attempt. So it'll try to cache as much as possible. But generally speaking, you work on the crate as a compilation unit. So if you want to speed up compilation for your project, what you want to do is you want to break it down into crates. It doesn't matter too much if the files are big or small, because the files are not a unit. So if you have a large project, you may want to split it out into vertical slices. For example, if you're doing domain-driven design, you may want to split it out in the different domains that compose your application. And then that domain functionality will span from the API layer to the domain logic all the way to your integration with the database. You may also choose to slice it horizontally. So you may have an API crate, a domain crate, and a DB crate. Or you could do both things at the same time. So you can slice it into user flows, and then each flow can be sliced down horizontally into the specific subcomponents. What's important is that you don't end up with a single crate with tens or hundreds of thousands of lines of code, because then your inner development loop will really take a hit in terms of speed.
Yeah, I think it was the Z Rust editor or IDE. It's not specific to Rust, but I was reading the source code there and it had everything in different crates and used Rust workspaces. Is that the sort of pattern that you mean?
Exactly. And you can see this in any sufficiently large open source Rust project. So Z is an example of that. UV, the Python package manager, if you open the UV GitHub repository, you'll see something along the lines, probably 20, 30 crates. If you open the Rust compiler itself, you'll see that it's split up into a lot of crates, probably in the 30s, if not more. I haven't checked it out in a while. But yes, like you want to try to make those units as smaller as possible without going too granular. This is very important. Like there are consequences to splitting things out into separate libraries. You can't access items from other libraries with the same freedom or the same level of access that you can access things in the same library if they live in different files. So you need to find the right boundaries. Otherwise, that's going to be a bit cumbersome to work with.
Oh, I'll get some show notes off you and put those links to the Python code base and that other one you just mentioned. Do you recommend that there would be individual separate libraries that would be crates on crates.io where you download packages? Or would they be a workspace within the same project? Or is that the same thing?
It's orthogonal insofar as if you're developing an application that's proprietary, that you need to deploy yourself as a binary somewhere, you don't need to publish your sub-libraries anywhere. More often than not, those wouldn't be open source. So you wouldn't publish them because you don't want the source code to be divulged. So you don't need to care about the registry. The registry is only something you care about if you need to distribute whatever you're building as a library or a binary for other people to use, and you want that to be open source. For example, I maintain a Rust framework called Pavex, which contains a binary called Pavex and PavexC. And these binaries are CLIs that you need to use to perform some tasks. Those binaries, to try to make them compile fast, I have broken them down into smaller libraries. Since I want to publish the binary to the registry, I am forced to also publish the sub-libraries to the registry. Because the constraint is nothing can be on crates.io, the Rust package registry, unless all its dependencies are. So even if those sub-libraries are not really meant to be used independently, they're not standalone libraries for you to consume, I still need to publish those to the registry because I want to publish the binary. But that's really a concern specific of open source software. If you're doing closed source development, perhaps in a company which has 3, 4, 5, 6 teams, you might have an internal registry, which is private, and you would publish there the libraries that different teams need to use across different applications, unless you're using a monorepo. So you might want to publish there your telemetry library. You might want to publish there some company-specific implementation of, Auth or some data store-specific bits. Anything that needs to be reused across multiple projects, it helps if it goes into a registry, either public or private, depending on your constraints.
Thanks. And do they always have to be in your workspace within the Rust project, or is that something you decide upon if you want to share versions and dependencies? Because that's what it means, isn't it?
Yes, that depends. As I said, if you're doing a monorepo, then you would do a gigantic Rust workspace with all the Rust things in one place. Otherwise, if you're doing a more classic development model where like different microservices, let's say, have their own repositories, then they would be brought into your project as dependencies from the registry. So they wouldn't need to be in your workspace. You would simply say, give me my company _ telemetry, and then you would specify that it comes from the name of the private registry so that it doesn't try to pull it from crates.io, the public registry.
And if we go back to the first part of the show, the Docker image doesn't care about this. We're just doing cargo builds. It knows what to do based on the TOML file we've got in our project, and it'll go off and find everything and do what it needs to do.
Correct. Now, if you're using a private registry, you might have to care about authentication probably. So your Docker image will have to have a way to authenticate with your company-specific registry in such a way that it can pull down the libraries it needs, because those wouldn't be copied with a copy statement because they wouldn't be in the same repository. But these are all annoying details that you can figure out, and the specifics depend on what registry you're using and how to authenticate, but it's all doable.
And earlier you said the debug profile was faster than the release profile. If we think about speed at the moment, do you have any rules of thumb of when to reach for these multi-crates or workspace type project setups? Or it's one of the first things you hear about Rust, or building Rust is slow. But have we got any numbers around that in your experience?
It's difficult to have numbers because it really depends on the type of code you're writing.
Yeah. Well, let's take your open source project you were just talking about.
Oh, yeah.
Can you remember what it was like before you split everything up?
It's difficult to make this comparison, right? Because it's not like it was the same lines of code.
Yeah, true.
And in general, it's difficult to, I wouldn't recommend going and developing a large project in a single library. Everything is entangled with everything else. Then splitting it up is going to be complicated. Generally speaking, what I would suggest is the normal good practice of software development. So even if something is inside a single library, try to have clean interfaces between your modules. At a certain point, when you decide the compilation is too slow, perhaps because a recompilation from a warm cache takes 30 seconds, that's a long time, or 20 seconds, that's still a long time, then you can say, okay, well, these modules that I've kept nice and self-contained, now I'll make that a library. You need to keep the modularity in mind as you are developing the project, because otherwise you need to go through a painful refactor to first change the internal structure of your library to have a clearly isolated module and then pull that out into library. It's not very difficult from trying to break a monolithic application. You need to have it structured in such a way that that is possible. If not, then you need to spend the time refactoring to make sure that then it becomes possible.
So we're going to get a gut feeling really when things start to get slow, because you'll have been writing that code since the start, so you know that it's getting slower and slower, basically.
Yes, exactly.
And is there anything in the container world that would help with a big build of a Rust project in the build layer, as it were? Or
when you're building Docker containers, you need to try to optimize for Docker layer caching. So all that we have said up until now about the inner development flow relies on incremental compilation. So Rust having a fairly detailed cache from what it did during the previous compilation attempt to try to speed up the current compilation attempt. When you are compiling in CI, or more generally trying to build Docker containers, incremental compilation is not going to be particularly useful, because a Docker layer is invalidated as soon as anything from the previous step has changed. So a technique that you can try to deploy is to try to cache your dependency tree. So you don't try to cache the intermediate artifacts of your libraries, the one that exists in your repository. You try to cache all the compilation work that was done for your dependencies, because those come from the registry. And as long as their versions haven't changed, they'll result in exactly the same intermediate compilation artifacts. So you try to structure your Docker build as a multi-stage build, as we were saying at the beginning, to try to have a step where you compile your dependency tree, then a step where you compile your application, and then you copy the final artifact into the runtime image. And as long as your dependency tree, so your log file, really, your cargo.log file, hasn't changed, that layer will be cached. So you're just rebuilding your projects, which is usually going to be a much smaller percentage of the total build time. And you should be able to push a Rust image to production in, a minute, perhaps, something along those lines. That's the target number I usually try to strive for, mostly because the time it takes to push something is very closely related to how long it takes you to patch an incident. So you want to keep that small. The specific project I will look into, which I maintain for doing Docker layer caching, and is the one used in the book, is called Cargo Chef. Cargo, the Rust package manager, doesn't support this local layer friendly layout out of the box. So you need a third-party tool to make it nice.
So the cargo.lock file and the cargo.toml file that you see in a normal Rust project, the .lock file is all your dependencies. So that's the trick you can do to speed up the Docker build.
Yeah, so the toml file is the specification. So it's about, I'm happy, for example, to get any dependency, any SERDI version, which is 1.0 or above. So you specify a Semver range in your toml files. The lock file contains the result of the version resolution algorithm. So the cargo, the Rust package manager, we look at all your toml file, we look at all your versions, we look at the version requirements of your dependency recursively until it's built the whole tree. And then it'll try to figure out a version for each library that kind of fits all the requirements. And it'll save that resolution into the log file. So as long as you don't explicitly change your dependency tree, either by updating or by introducing new dependency or by removing dependencies, your log file will stay stable. And so as long as your log file stays stable, the exact dependencies that you're pulling in won't change. This is very similar to log files in other languages. I think JavaScript has a similar concept. Python has several implementations in this for different package managers. So it's the split between what I want and what I get.
And you said you need Cargo Chef to be able to do that in
You need Cargo Chef to be able to take a cargo lock as input and just build the dependencies without building the local packages.
Cargo build wouldn't do that by itself.
Cargo build will build the whole project. So it will build all your dependencies and your code. But it's safe to assume that if you are building a new image, it's because your code has changed. So if you're doing in Docker a copy ... which is bring all the files into the image, and then you do a cargo build, what's coming in via that copy has certainly changed with respect to the previous time you tried to build the Docker image. So that would result in a Docker layer cache miss. And so your cargo build would be building fresh. So you would always be starting from scratch, which is
It's a really good hack, isn't it? As they say, for speeding up Rust project builds.
Some would say that it would be nicer if Cargo supported something of the sort natively, and I do concur. In the meantime, I put together a solution to kind of stop the bleeding for my own commercial projects.
Perfect. That was quite a deep dive there. I wasn't expecting that. I really enjoyed that. I've got a few questions left in this section before we move on, so we'll maybe have to be brief on them.
Sure.
So what key components do we need to think about, given the fact that our newsletter app is going to be on the internet? With specifics to Rust, I don't think there is anything unique about this application versus another API application written in a different language, would you say?
Yeah, I would say there's nothing specific to Rust as to what you need to be aware of when it comes to the exposing something on the internet. The same core principles apply. So you need to have some kind of network topology. So make sure that you're only exposing the ports that you're planning to expose. It's good practice to make sure that all the ports you're exposing to the internet are protected by TLS, Transport Layer Security. So you want to use a platform or provision certificates that the browser could verify. And then you want to make sure that your image contains the minimal amount of things that it needs to contain to minimize the security surface. So that if somebody were to be able to somehow gain remote code execution on your application, they wouldn't have too many tools to leverage. And you also want to contain what they could do. So you also want to lock down what your Docker image is able to connect to. Those, I would say, are the key principles. And then the second is you want some kind of access control on all the operations that your application exposes, which are privileged. So if you're looking at our newsletter application from the book, you need to be able to send a newsletter. That means we need to be able to verify that you are the owner of the newsletter, which means we need to log in. Every time you're trying to implement a login, then you have a cascade list of security requirements. There's various vulnerabilities you need to be aware of. You need to protect around CSRF, cross-request source forgery. You need to protect against man-in-the-middle attacks, answer requirements for TLS. You need to store password in a safe way. So all of these things are not Rust-specific. And this goes back to what I was saying at the beginning. We're not breaking new ground here. It's about how do I do these things in a Rust application? And that's a challenge specific to the fact that Rust has a small standard library too. So in other languages, I think of Go, the solutions to a lot of these challenges can be found in the Go standard library. That is not the case for Rust. Rust adopts the philosophy of having a minimal standard library and pushing these concerns to the ecosystem, which then poses to you, the developer building an application, the challenge of what do I use from the ecosystem? What can I trust? Do these building blocks play nice together? Is this better than this? And so those are some of the questions that the book tries to answer. And more than answer, trying to give you the tools to answer those questions yourself in the future for other types of tasks that you may need to reach out for to the registry.
We did a show, episode 383, all I did with Neil Madden on securing your API, which I highly recommend. That covers a lot of what you just mentioned as well. Is there anything specific to Rust, given the fact it's strongly typed? So if we're taking in, say, a JSON payload to act on for the newsletter subscriber, adding them or something, and say there's a problem with taking that JSON in and converting it to a Rust enum or structure using SERDI that you mentioned earlier, the serialization and deserialization library? Or is that just something we handle in our error checking and all that type of stuff?
There's two steps to that. The first one is we need whatever code is doing the deserialization to not have vulnerabilities. And that's about, do I use SERDI? Is SERDI like a well-audited crate? And are we sure that SERDI and the specific format deserializer we're using, in our case that would be SERDI JSON, do not cause any vulnerabilities if the payload is maliciously crafted? The second layer is we need to handle that deserialization error. This is usually quite simple, so far as if something fails to deserialize, you would return a variation of a 400, and then you just craft a good error message. So it's not like, the good thing about Rust, and actually the appeal of the language, is that you can make safety modular. So since Rust protects you as a language from a variety of memory and safety vulnerabilities, as long as you stick to safe Rust, so you're not using the unsafe portions of the language, the one that let you do some pointer wrangling and other more manual memory operations, you already know that a bunch of issues that you may have, like buffer overflows, out-of-bounds access, if you're trying to access an index that is beyond the end of an array, and similar bridgeheads, problems that attackers would use to then jump from there to remote code execution or other kinds of exploits, you already know that those are patched. So usually you can focus on the logic of your application and not have to worry too much about these things, as long as you made sure that the dependencies you're using haven't introduced those vulnerabilities by incorrect usage of unsafe Rust. So that's why this goes back to, you need to audit your dependency tree and be very careful into what you bring into your source tree.
This comes under that umbrella that's been spoken about quite a lot over the past few years, the supply chain, isn't it?
Supply chain security. Yes.
Yeah, with all the big things that have happened past couple of years.
And I mean, there's two aspects to supply chain security, I would say, right? One aspect is, are the people I'm trusting trustworthy? So do I fear that at a certain point, one of my dependencies might turn rogue and push code that is intentionally malicious? And so this is one part. The other part is there a bug that is, undetected? It's not maliciously been planting there, but it's in my code, it's running and exposes my application to vulnerabilities. Those are two different type of concerns.
There's always a bug, isn't there?
The problem is it a security vulnerability bug or not? Yeah. And, that is a concern that varies depending on the type of library we're talking about. The library does serialization, deserialization. I mean, it's a prime target. Like everything that touches untrusted user input needs to go under extreme scrutiny. That's not the case for everything else that's inside your code. But yeah, anything that's on that network boundary, the implementation of transport security, the way you parse HTTP requests, the way you parse the bodies, all these things, those need to be hardened and they need to be battle tested.
Thanks. So I've got a few questions left in this section, like I said. One of them was, where does our application live? I think we've touched upon that by explaining that we're going to put it in a Docker and pop it on the cloud somewhere. How do we get it there is also covered by that, whether it goes through our CI pipeline or... Well,
we push an image somewhere and then the platform makes it so that it goes to the right place. In the book, we use DigitalOcean because it's simple and convenient, but the specifics will vary depending on if you're deploying to AWS, if you're deploying to Azure, if you're using Terraform. So the options are endless. As long as you build your image, the rest is language agnostic, I would say.
I was going to ask, how does this compare to other languages? But it's the same. It's the same. It's the image. So the last one in this section before we change, do you have any performance metrics that would be normal for a back-end Rust application like this one? As in, let's say we built it in another language, the exact same thing, in the exact same DigitalOcean with the exact same Docker build setup. can we just love the fact that Rust is going to be so much faster, or is that still something we need to think about as a software engineer?
So as long as you use the same architecture, so we're roughly, as you said, implementing the same application in the same way in different languages, and we're comparing, let's say, Rust to Golang, Python, Node, to use or Java, to use some commonly deployed backend applications as a reference. We generally would expect the Rust application to outperform them, but let's be specific as to what that means. One point we touched before, so your Docker image is likely going to be smaller, probably going to be comparable to Golang, but generally speaking, you're deploying a Docker image that it's as small as it could possibly be, which means that it'll be faster to roll it out, it'll be faster to scale your software up and down, because whatever is running the Docker image will take less time to pull it. After that, there's three main performance metrics that we'll look at. One is how many requests per second can we handle on a given hardware, how much memory are we using, and what's the variability in our latency. So what's the difference between, in jargon, what's the difference between our 50th percentile in latency and our 99th percentile in latency. So let's start from requests per second. In my experience, generally speaking, if you're building an API, you'll sooner run into your database not being able to keep up than your Rust code not being able to keep up. Because the Rust code is going to be fairly efficient. Most of the time it's going to spend doing I/O. Rust is a very efficient async I/O model, which allows you to multiplex multiple tasks concurrently over the same CPU core. So you're not going to be bottlenecked on CPU work. So it really is about optimizing access to the data store. And in this, it's not particularly unique. Same problems you will have in different languages, which are reasonably efficient. The difference is going to be in memory usage. Rust is fairly parsimonious when it comes to memory usage. And most importantly, tends to clean after itself. So every time some value is allocated, when it goes out of scope, it will be immediately deallocated. And that's because the Rust compiler knows where things are live in terms of values. This makes it so that usually Rust applications have a very small memory footprint. So if the Rust application isn't doing any work, it's going to hover around, usually the number I see is around 40, 50, 60 megabytes of memory usage. It'll go up proportionally to the amount of traffic that's coming in. And then once the traffic goes out, they'll go back down. So it's fairly easy to do resource planning because it's very proportional to the work that's being done.
That's a really big advantage, isn't it?
Oh, it's a massive advantage, especially operationally. Like you can look at a graph, like the key system metrics of a Rust application. So how much memory am I using? How much CPU am I using? What's my P50 and P99? And you'll see that generally, like they move together with respect to the number of requests. This is assuming they were talking about requests to do the same thing or roughly the same amount of work. So that makes it easy to plan how much headroom you need, makes it easy to understand when the application needs to scale. So if you need to configure an autoscaler, it's easier to know what thresholds to set. It also makes it easier to understand if something is wrong. Like if you look at your P50, your P99, and the time spent inside the Rust application, so let's exclude the variance that comes, for example, from the data store, usually they'll be pretty flat, like the band will be pretty tight. So if you suddenly see spikes, that's a sign that something is wrong. Now, generally speaking, all of these are generalizations. They depend on the specifics of your application, but I have deployed Rust applications quite extensively. Previous workplaces, Layer, as an example, used to have a variety of languages in production, a lot of C#. And we have seen that the footprint of Rust in production is significantly smaller, to the point that our compute bill was a fraction of the compute bill for the C# applications, handling more or less the same traffic because we were part of the same microservice architecture. So generally, like you'll get efficiency out of Rust. Caveat, keep an eye on your data store. Sooner or later, that will be the bottleneck.
Seems to me that Rust is a very sort of green, energy efficient language as well.
Yeah, I mean, if we consider the amount of processing power being used, then Rust will lower that, which in turn will lower the energy consumption of your applications. So anything that improves efficiency is going to result in a cleaner system.
Did we cover the three metrics that you were going to talk about there?
Yeah, I would say so. So latency, CPU, and memory usage.
Yeah, the P50%.
Yeah, P50 and P99. So for those who haven't heard of this before, it's half of your user will see a latency that's below the P50, and 99% of your users will see a latency that is below the P99. the closer the P99 and the P50 are together, the more you can reason about the average experience that somebody's having using your API. And so it's ideal for a system to have very close bands. So to have a P50 that's very close to their P99, because that makes it uniformly reliable for people to use, makes the experience very consistent. And so since Rust has that very predictable pattern of memory allocations and deallocations, that usually makes it so that doing the same amount of work takes the same amount of time, unless the application is under too much load. And that will make it so that, your P99 will be reasonably close to your P50. And this will make it easier to scale your software. The important aspect here is that Rust doesn't have a garbage collector. I'm surprised I haven't mentioned that so far. So since Rust doesn't have a garbage collector, there's not going to be sudden spikes in your P99. Like, you're not going to find out that mostly it is consistent, but from time to time, we're going to stop the world, in quotes, and collect a bunch of garbage. And so our application will be busy doing that. So it won't be serving requests that are coming in, and those requests will be slower. That is a problem you'll see in C#, a problem you see in Go. It's been multiple articles. I think one of the most famous ones is the one from Discord, moving some services from Go to Rust, precisely because of this reason.
Yeah.
So the lack of a garbage collection feeds into that predictability.
We're going to talk about telemetry. Let's assume everyone knows what telemetry is. I'll have a go. Sending stuff from your app to somewhere else so you can see what's going on. Is that?
Yep, that's a reasonable.
What options do we have in the Rust ecosystem for this?
So Rust has a fairly established library for collecting telemetry data. It's called tracing. And it works similarly to how you may have used logging in other languages. I think of Python as a reference example. There's an interface, call it a facade. So it gives you a bunch of methods to record data, like log at the info level, log at the warn level, log at the error level. And then you can configure your application to process that telemetry data in different ways. So you can install different subscribers, and they will process this data and ship it off to the terminal or Datadog or Honeycomb or whatever you use for then querying, searching, sifting through this telemetry data. The good thing about Rust, once again, is that since the language is compiled and it's using like a wide range of applications, so from embedded to the cloud to the browser, the tracing library is optimized for minimal overhead, which makes it so that whenever some, for example, log lines have been disabled, runtime or compile time, the cost of those is going to be minimal. So you can be pretty liberal in instrumenting your application. And then it's about setting the right log level, and you can raise it as necessary if you need to get more telemetry data. The rest is language agnostic. The golden metric, like the golden goal that you want to achieve, is that you should be able to troubleshoot your application based on the telemetry data you are collecting. If something happens in production, it's a bug, you know it's a bug, and you look at the logs and you have no idea what that is about, and you need to deploy new logs, that's game over, like you failed. So the idea is we need to make it so that all the logs are there, that we're capturing the key information, and then we can raise the log level as necessary. In the book, we do it with the OpenTelemetry standard. No, we do it with JSON logging. Usually in production application, I would do it with OpenTelemetry, which Rust supports. And that would allow you also to kind of link all this instrumentation across network hops if you have a microservice architecture. But as you said, like, it's not really important where the logs go. The important thing is that they contain in the first place the information that we care about.
And you talk about, I think you briefly mentioned it just then, but the Facade pattern, is that how you say that?
Yeah, the Facade pattern.
Facade, yeah. Of course, that's how you say that word. Sorry.
French, I guess. Yeah, Facade pattern means I'm going to give you an API that's going to be the same. And then underneath that API, you can plug different backends. That's the most commonly deployed way of doing logging across most languages. The logging module in Python, as I was mentioning before, does the same thing. So you always use the same functions. And then at the beginning of your application, when you are initializing all the things, you also initialize the logging backend. And Rust uses the same pattern.
So our takeaways from any type of telemetry in Rust is that we reach for the tracing crate or library, and that it's really optimized for browser back-end, front-end, because it's heavily used, and it doesn't have any runtime or compile time downside if we disable a logging or enable.
It has minimal runtime overhead. It cannot go to zero, but it goes as close to zero as possible.
So there's nothing we need to be unconfident about putting that in production.
No, nothing you need to be concerned about. Obviously, the log lines that are going to be logged, they're going to have a cost. So if you are sending log lines in the several megabytes ballpark of size, exporting those is going to be expensive. So you need to keep in mind what data is being pushed and being pushed where. But other than that, you can be pretty liberal with having like trace level, debug level log statements, which are a bit more expensive, which are disabled usually, but you can enable on the fly if you need to debug further.
And does the trace and create give us what you call, or what is commonly known as structured logging, or is that something different? And what
it's exactly that.
It's exactly that, okay.
So you get log messages, each log, so you have a span. So by default, when you're capturing something, you can capture its duration. So you can capture when it begins and when it ends. It has a level so that you can do filtering based on the level. It has a location. So it tells you where that span is coming from. So you can say, give me info level logs from my application crate, but give me only warm level logs from the HTTP dependency that I use to parse dependencies.
And the span's important because of multi-threaded.
The spans are important. Multi-thread is more of, you need to be careful with that to make sure the spans are correct. But spans are important because they give you a logical stack trace. So you can understand if something happened inside a certain span or outside, and they give you the duration of an operation, which is often very important information when troubleshooting. And the other thing is that you can capture fields. So name fields, key value pairs, which if you then export to something that has support for searching them, allows you to do structured queries against that data.
That's good to know. Rust is a first-class citizen with open telemetry as well, trace and create, isn't it?
Yes.
Okay, so last section, error handling. In our app, what errors could we get?
All sorts. So we could, as we mentioned before, fail to deserialize the payload that's coming from the user with the request. We could fail to talk to the database. The database may not be there. The database may return an error when we query it. The database may return data that has a shape that is not what we expected. We may be failing to talk to our email provider to send a verification email. So things can go wrong. Like that's an endless list of things that go wrong. Now, the cool thing about Rust is the way you model that behavior. So in most languages that I've personally used, and I would say most languages that are currently used in the industry, errors are modeled as exceptions. So that's the case for Java, it's the case for C#, it's the case for Python, etc., etc. Exception go through an exceptional control flow if you want. So when you are programming, you don't really see exceptions. They jump through the different function calls in your stack trace, and you need to be explicit about trying to catch them. It's a very non-local type of error handling. So something very deep in your call stack may raise an exception that you're handling 6, 7, 15 layers up. The problem with exceptions is this non-locality. When you need to recover from the error, so as long as you don't care, you let it bubble up to the top, return a 500 and log it. That's the easy part. The complicated part is where you need to do different things depending on what error has occurred. And so you then need to say, okay, I need to catch it. I need to catch it with the right type of exception. And that may happen in a different place. And so when you change the location where the error is emitted, perhaps the error type changes, but you forget to change your try catch somewhere else. And then suddenly your error handling flow is broken. If you have a test, you may catch it. If you don't have a test, that's a bug that goes straight to production. Rust, like many functional programming languages like OCaml, Haskell, and the likes, instead models errors as values. So you have a type called result. It's a Rust enum, so it has two variants. The OK variant returns the data in the case the operation was successful. The error variant returns an error in case the operation was unsuccessful. The error is typed, just like the OK variant, so you can have different error types that contain different error information, and you can't access the success value unless you specify what to do in the error path. So you're always forced to handle the error case if there is an error case. Handling the error case usually means using a match statement. So specifying two code paths, one for the happy case and one for the error case. In most situations, you want to bubble up the error. So you want to return an error from the function that kind of contains the other error as a source. Other times, you may want to log it, you may want to swallow it, you may want to do some default logic. But since all of this is explicit and captured in the type system, if the error type changes, if a new failure mode is introduced, very often your code will fail to compile. So the Rust compiler will tell you, hey, here you said that you're handling the case where the record is not found. But now there's a new error. There's also the case where the connection fails to be established. You need to tell me what to do in that case. And this makes it so, generally speaking, based also on my professional experience, the software written in Rust tends to be more stable when it comes to error paths, because the type checker is doing a lot of the heavy lifting for you to make sure that you're not forgetting things along the way. And that's exactly what we do in the book when trying to implement the newsletter. We try to structure good errors. We try to use enums to explain what the different error cases are so that we then can handle it in a structured way where necessary.
And does Rust give you an escape hatch if you just don't want to handle the happy path and the error path?
You would bubble it up. So you can do that. There's a little bit of syntax sugar. It's the question mark operator where you say, this thing can fail, question mark. The question mark means if this function returns an error itself, then bubble it up as an error to the caller. And that usually works automatically as long as the two error types are compatible. So the error type you are bubbling up can be converted to the error type that the current function returns. And that would go up all the way, usually to a middleware somewhere that's going to convert it into 500 and log it.
Yeah, with specifics to the API that we want to return to the user. Okay, I'm going to move us along now. You talk about an internal error and an edge error. Is that something specific to Rust or just to this back-end application?
I would say it's a general software development pattern. When you talk about edge errors, you're talking about the error conditions that the user can see. So this is the contract of your API, if you want. If I call this endpoint, what responses may I get back? And most API documentation will usually be very thorough in documenting the API case, but will usually under-document the API case. So there list some error responses, but a few more may come up in practice. So you want to be very careful in designing those edge errors, because those edge errors need to satisfy different requirements. So they need to enable very often some kind of control flow on the user side. So if I'm calling an API and I get an error, I need to determine, is this error fatal? Like if I retry, may I succeed? Or will it always keep failing? So you need to give them some machine readable information to make that determination. So we do that with status codes very often. So you know that if you get a 400, retrying is not going to make it succeed. It'll keep failing because the request is malformed. If you get a 500, sometimes that means that you may succeed if you retry. The application can be well behaved and give you, for example, retry after header that explicitly tells you, retry, please let's wait a certain amount of time. We're having a rough patch, we'll recover. If you get a request conflict, that may succeed if you retry. So it's about making so that you are giving structured information to the caller so that they can build their own control flow and make it so that they can automatically recover in the cases where that is supported, or themselves escalate to an operator in the cases where that's not going to be possible. So if you get a 400, there's a bug in implementation. Like a developer needs to go and look at it and fix the payload that's being sent. The other part is about explaining what is wrong. So if you give me a 400, it's like, okay, cool, my request is malformed. How? Like what's wrong about it? So you also need to have information that's geared towards the operator that's going to try to handle this failure to troubleshoot it, to fix it. So you usually want to say, well, we expected a field name X, the field is not there. And we expected a field name email that contains a string, but your field name email contains a number. That's not going to cut it. So that kind of information needs to be in the body.
And that's something Rust can help with because of its really
strong modeling.
Yeah.
Exactly.
Are there any Rust practices that we would use in our day-to-day programming life that we shouldn't use in production with regards to error handling?
A more drastic escape hatch is instead of bubbling up the error, you can panic. A panic in Rust is equivalent to crashing the program. With some caveats, you can catch some panics, but generally speaking, it's meant to be a non-recoverable error that's going to drop the connection and just unwind the stack. So when you're doing some prototyping, very often just to try to validate an idea faster, it's good to just panic on errors. It's like, yeah, sure, I'll handle this later. Don't want to ship that to production usually. You want to clean it up first.
And is that unwrap as well?
Yeah, that's exactly what unwrap does. Is this may fail. If it's an error, panic. Otherwise, give me the API case.
Perfect. So this is a bit specific to your career. You might not be able to give me any detail in your answer, but have you seen any Rust code in your career that you just want to change and rip up immediately before it goes to production?
I've seen a lot of code that I wanted to change before it went to production in many different languages. This is not specific to Rust, I would say. Sometimes you need to develop under time constraints that don't allow you to produce the level of craft that you'd be proud of. I guess that's a fairly common experience.
Are there any tools in our beautiful, wonderful Rust ecosystem that can help us go through the code base and go, hold on a minute, if this going into production, you're going to have problems?
Yes. So Rust ships with a default linter called clippy. And clippy tries to catch a lot of problematic code patterns, usually as a warning that you can choose to then respect or ignore. It is good practice or recommended run clippy in CI and make it fail on warnings.
That's what I do, yeah. In fact, I used a bit from your book in one of my own projects.
Yes. And then, sometimes you can ignore the warnings. Sometimes the warning is not important, but at least you need to think about it, which is a good point of reflection.
Have you tried the 2024 edition of Rust yet?
Yeah, I've already migrated a bunch of projects.
Yeah,
pretty uneventful migration, I would say. A lot of the tooling does it for you, so it wasn't too much of a lift.
I've been working on the 2021 Rust edition mainly because it's 2025. And when that came out last month, I switched it on in my own project, which is a blend of C and Rust. And so my big work bit is to put unsafe keywords everywhere that I didn't need before.
Yes, they tied in the screws a little bit on unsafe blocks.
And that's good. Yeah, it's a bit of a chore. Okay, so to summarize that, there's always bad code before it gets to production, but Cargo Clippy can help us clean up a lot of that.
And coverage, I would say. Test coverage is always a good thing to keep a handle on.
Yeah, I saw that in your book about test coverage. Was it the LLVM?
You can use an LLVM cov, yes.
Yeah, that's what I took from your book and put that in my own project too. Because there's not much on the internet about Rust code coverage, what tools to use.
It's been fragmented because historically the approaches were different. Then the compiler gained support for emitting LLVM coverage information. And now that's the fastest way to get coverage.
That was really good. Very happy we did this show. And I hope that helps others understand, like it did with me, how we take a Rust application from our desktop and get it into the cloud, what to pick and what not to pick, and all the tools out there to clean things up. Even though we did a good deep dive on a lot of topics, was there anything you think we missed that we should mention before we finish?
I would say this was pretty comprehensive. I'll make sure to provide show notes for some of those deep dives so you can go and read further. But other than that, I think this was a good representation.
Yeah, I think we should definitely put a link to your open source project and just see how you do it properly. That'll be the one to read and everyone to copy.
That's a lot of pressure.
Nah. It's open source. It's always out there in the open. How can people get in touch or reach out if they would like to speak to you or tap into your expertise?
Most social media platforms, so you'll find me on Blue Sky, Twitter, and the likes. And that's my website as well, which has contact informations.
Luca, thank you for coming on the show. It's been a real pleasure. This is Gavin Henry for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.